Hello learners, BME 025 Condition Monitoring and Maintenance Management, video number 14 Trend Analysis, presented by myself Dr. N. Venkateshwarlu, Associate Professor, School of Engineering and Technology, IGNOU, New Delhi. In last video we have talked about the failure rates, but here we will talk about the failure costs. The costs involved in machine failure analysis. While analyzing the machine failure, we are concerned with the following costs: purchase cost of the machine or equipment capital investment, depreciation or salvage value or scrap value, running costs including maintenance, repair and operating costs, failure costs and damage costs. In the above four, the first three are inevitable, but the failure costs can be prevented by better maintenance policies. On critical examination, we can notice that the first three costs depend on age of the machine. These costs vary with the running age as follows. Purchase cost of machine or equipment is considered to be independent of age of machine. However, the interest on the investment is assumed to be lost. Resale value or salvage value or scrap value of the machine decreases with the running age of the machine. As the machine grows old, its resale value comes down. This decrease depends on actual or expected condition of the machine. C. Running cost or operating cost of maintenance cost of the machine is due to its minor failures or preventive maintenance or operating costs, etc. These will increase on the machine as the age grows. This is assumed to be increasing due to the wear and tear on the moving parts of the machine. The above costs are shown graphically on the hypothetical machine here below. That is, in the units you can read it. The figures you have to see. Summing the above three costs, we can notice that the average total cost decreases for the certain period and then increases. The age, when the graph shows its minimum cost, will be optimum age of replacing the machine. Necessity or significance of replacement. So, replacement policy. What is the necessity? What is the sequence of the replacement policy? The replacement of parts or entire machine will become significant and necessary in the following cases. In which cases it has the replacement policy has to be adopted. So, which are: A. When average cost of the repairs or maintenance or operating goes higher than the cost of the machine, or in other words, the cost of maintenance will increase to such an extent that the average annual repair or maintenance cost is greater than or equal to cost of new machine. So when we have to repair or when we have to recondition the machine, so if the reconditioning cost or repair cost is not more than the new machine cost, then only we can adopt the any maintenance policy, or otherwise we scrap that machine and we can purchase a new machine. The machine runs with less efficiency and therefore not economical. So this is also one of the reason. When the machine completely fails to work very frequently, by which the production schedules are interrupted. If it is D, if it is expected that the existing model may become obsolete, resale value may drastically come down. So during such type of, these are the various reasons. During these reasons, if the machine belongs to, then the replacement policy can be adopted, or replacing that machine and purchasing a new machine. And E, modified or new design in the market may give an edge of advantage, such as reduced cost of production or ease and comfort of operation, or more functions are available in new designs, etc. If the item is non-repairable type or use and throw type, then we go for the replacement method, replacement policy. So now we have learned about the replacement methods, cost of the machine, depending upon the cost of the maintenance and cost of the maintenance trend, or the depending upon the value of the repair cost will be, if it is more than the or a new machine cost, then we go for the replacement analysis. So for that we have to learn about the trend analysis, what trend of that machine is, then we can able to understand the trend analysis. The main objectives of trend analysis is directed to know whether the equipment is deteriorating or improving. This can be known by analyzing the past failure data in terms of TBF, or time between failures in case of repairable equipment, or TTF, time to failure in case of non-repairable equipments. From the analysis, one of the following three conclusions may be drawn. Positive trend, if it is a positive trend, then what will be the policy? So positive trend implies that the machine is improving with time. So once we are using, that efficiency is increasing. So that is the positive trend. This may be due to the machine is new or infant stage, that is first stage of bathtub curve, or effective maintenance. It is observed by gradual decreasing failure times or decreasing failure rate. So failure rate is minimum. Here the machine will work optimally. The machine will work without any interruption, or you can say that minimum failures. The failures will be reduced when it is going on increasing working and its time is increasing, but its the failure rate is decreasing. That is positive trend, you can say that. Then negative trend. If the machine is showing a negative trend, it implies that machine is deteriorating with time. In other words, the equipment is subjected to frequent or long failures. It is indicated by gradual decrease of failure times. So it's a negative trend, means the machine is showing a negative trend. It implies that machine is deteriorating with time. If time is increasing, the deterioration also increasing. That is known as a negative trend. So it can be considered that machine showing negative trend is in the third stage of machine life cycle or old age. It is due to worn out parts or inherent failures or inappropriate maintenance systems. Whatever the reason may be, the situation disrupts the production and affects the productivity. Therefore, such equipment is of more concern to maintenance as well as production engineers. These failure patterns are categorized by increasing failure rate. So this is known as a increasing failure rate. No trend. So there is no trend. First we know that we learned that one is positive trend, then negative trend, then no trend. So this is one of the critical situation maintenance engineers face. If failure times are neither increasing nor decreasing, it may lead to conclusion that the equipment is experiencing constant failure rate. But it is true in some cases only, which means that the no trend situation need not be youth or a random failure with constant failure rate, with a constant failure rate. So however, the no trend situation implies that the failure behavior is independent of time. It may be in random failure stage or typical increasing failure rate due to independent and identical distribution of failure times. Therefore, this rate is to be further analyzed to know this fact. So we have to understand the trend. So methods of trend analysis. There are various methods of trend analysis. So trend analysis is carried out in basic ways, that is graphical and analytical. These methods are described below. Graphical methods for trend testing. The following two methods are most popularly employed graphical methods for monitoring monotonic trend. cumulative plot test and eyeball test. These are the two methods for trend analysis. Cumulative plot test. This is most powerful test and gives easy understanding because of its pictorial nature. To perform this test, first of all, the times between failures of the equipment is collected in chronological order. The cumulative time between failures are then calculated and plotted against the cumulative number of failures. By the presence of trend in times between failures, we means that whether the equipment or the item is deteriorating or improving with age. By simply plotting cumulative times between failures against the cumulative number of failures, we can test whether the machine or equipment under consideration is improving or deteriorating. If we get a curve concave upward, note that the opposite characteristics in TTT plots. This means that the times between failures are becoming shorter and shorter. That is to say, the machine is deteriorating. On the other hand, if we obtain a curve concave downwards, if we obtain a concave curve downwards, this means that the machine is improving. The data which exhibits linearly can be considered to have no trend. Such trend plot is known as exhibit independently and identically distributed data in statistics and has to be further analyzed by statistical distribution. Then next one is eyeball analysis. This is a simple analysis of testing presence of trend. In this, we pass our eyes through chronological times between failures and search for the increase or decrease of the failure rate. That is, if the times between failures are showing increasing failure magnitude towards the end, it shows decreasing failure rate. If the magnitude of times between failures decreases towards end, then it indicates increasing failure rate. If the magnitude of times between failures is approximately constant throughout the period, then it shows constant rate of failure. A slight modification can be done to this test. First, tabulate the cumulative frequency and divide the total period into equal number of parts, usually from 5 to 10. The class intervals can be judged by using Sturge's formula. Then find the number of failures in such periods of operation. If there is increasing number of failures for each period, then it indicates increasing failure rate and so on. Further, this can be easily judged by fitting a linear trend line, that is analytical trend tests, Laplace test and ML HDBK 189 test. So Laplace test. This test is highly useful for distinguishing between an HPP and a monotonic trend. Its high degree of occurrence keeps in top position of all trend tests. However, it is tedious and cumbersome to calculate, particularly when the data is large. Further, it requires the calculation from the beginning at every time, while the graphical test can provide instant answers at any point of the data. We will discuss the specific situation where one system is run until a pre-specified number of failures M has occurred under HPP assumption. The first M-1 arrival times T1, T2 and Tm to L are the order statistics from the uniform distribution on 0 to Tm. Hence, the test statistics are the equation UL is equal to 1 by K sigma I1 to K Ti minus T by 2 divided by T under root 1 by 12K. So this is an equation to find out the test statistic. So approximates a standardized normal variate, the approximation being adequate at the 5% level of significance for m is equal to 4. That is, in the equation 7.1, k is equal to m minus 1 and t is equal to tm. If observation stops at the last failure, k is equal to m and t star is equal to the time at which the observation stops. Otherwise, at significance level, there is evidence of trend if UL greater than Z alpha by 2, that is reliability deterioration. UL less than is equal to minus Z by alpha 2, that is reliability improvement. So compare the calculated U values with normal variate at 10% level of significance. If calculated value is within minus 1.6452 plus 1.645, accept the hypothesis, that is no trend, else trend exists. At 5% level of significance, the critical values are minus 1.962 plus 1.96, and 1% level, the critical values of normal variate are minus 2.582 plus 2.58. So in the MIL HBX 182 test, the test is based on test statistics. This is the formula. U is equal to 2 into sigma I is equal to 1 to n minus 1 in T n by Ti under the null hypothesis of HPP versus V is distributed as chi square with 2 into m minus 1 degrees of freedom. If calculated, chi-square value is less than chi-squared table value at 2 into m minus 1 degrees of freedom, 5% level trend is present, else no trend. So for degrees of freedom V greater than 30, the quantity under root 2x square minus under root 2v minus 1 may be used as a normal variate with unit variance. That is, z is equal to under bracket under root 2x square minus under root 2v minus 1. If calculated z value is in the following range of table critical values, then trend is present, else no trend. Critical values normal distribution tables are minus 1.64645 plus 1.645 at 10% level of significance and minus 1.962 plus 1.96 at 5% level of significance and minus 2.582 plus 2.58 at 1% level of significance. The test for presence of correlation. It is important to test the successive interval times for independence by testing them for a serial correlation. To test the data for serial correlations, I minus 1 TBF times between failures are to be plotted against the times between failures of the data. If the plotted points are randomly scattered without any pattern, it can be interpreted that the TBF are free from serial correlations. Test for presence of correlation. It is important to test the successive interval times for independence by testing them for a serial correlation. To test the data for serial correlation, I minus 1 times between failures are to be plotted against the ith TBF of the data. If the plotted points are randomly scattered without any pattern, it can be interpreted that times between failures are free from serial correlation. Testing for the presence of serial correlation before modeling the reliability data, it should be tested for the mutual independence by testing it for a presence of serial correlation. The presence of serial correlation can be tested by plotting the ith times between failures, say xi against the I minus 1 TBF xi minus 1. If the plotted points are randomly scattered without any pattern, it can be interpreted that the TBF are free from serial correlation. In case the plot reveals serial correlation, then the times between failures should be plotted at greater lags such as xi against xi minus 2 or xi minus 3, etc. To search for serial correlations over greater lags, Bundle and Wall 1985. Analysis with coefficient of correlation test. The data can also be analyzed with the Carl Pearson coefficient of correlation test between ith versus 1 minus ith times between failures and ith versus I minus second and so on. The degree of association can be calculated with the value of the coefficient of correlation that ranges between minus 1 to 1 via 0. The value nearing to minus 1 can be understood as the negative close association, which means that the increase in the first quantity induces a decrease in the second quantity. If the value is near to plus 1, it means that there is proportional increasing correlation between the quantities. If the value is near to 0, it indicates poor correlation, which means that the quantities are independent. So, analysis of data free from trends and correlation. When the data are free from the presence of a trend and serial correlation, the next step is to choose a best fit probability distribution model using total time on test TTT plots or goodness of fit test to study its statistical characteristics. Both graphical and analytical goodness of fit methods are used for this purpose or explained in the next units. So, first taking an example, the failure data in terms of times between failures in hours is obtained for a equipment in a process industry as follows. Conduct the trend analysis using cumulative plot test, eyeball test or serial correlation or coefficient of correlation. So this is the solution. The data for cumulative plot test and eyeball analysis shown in the following table. Relevant to calculations are shown in the table itself. So TBF is equal to times between failures and CTBF is equal to cumulative time between failures and OTBF is equal to ordered time between failures. After calculating the values, you can see that all the values are given. So like this, one has to calculate by putting it in the equation, we can calculate the times between failures, cumulative times between the failures and OTBF. So thank you. I hope you understand about the trend analysis and what are the various types of trend analysis and how the trend analysis will help in adopting a best maintenance strategy. Thank you.